Hola, Mr. Sutton here with the AB Calculus 3.9 Extra Practice Number 5 solutions on tangent lines and higher order derivatives. For this problem, we have a twice differentiable function y equals f of x, and we're told that f of 1 is 3, and that the first derivative is this crazy looking formula over here. We want the value of the second derivative at x equals 1. Alright, well, let's get a formula for the second derivative before we do anything else. So if we think of this as 4 times parentheses y squared plus 7x squared to the 1/2 power, then d squared y over dx squared, the second derivative, using the power rule, if we have 4 times something to the 1/2, that's going to be 2 times something to the negative 1/2, and then we have to multiply by the derivative of the something. Well, we have the derivative of y squared, which we're going to have to implicitly differentiate here because y is a function of x. So this would be 2y dy over dx. And then we'll have to add the derivative of 7x squared. That's going to be 14x. And I am about to plug some things in here, but let me clean this up a little bit first. So this y squared plus 7x squared to the negative 1/2, that can move downstairs as a square root. And then I'll distribute this 2 to the 2y dy over dx and 14x to get 4y dy over dx plus 28x upstairs. So we've got that upstairs, and all this stuff is square rooted downstairs. Because I'm going to have to evaluate this eventually anyway, I might as well know what I'm looking at. Now, there is one thing I need before I can start plugging things in. I mean, I have my x value, it's 1. 3 is my y value, which I'm also going to need. But notice we have a dy over dx hanging around in there. So we need to know the value of dy over dx specifically at 1, 3. So let me go ahead and find that. Now the good news is they gave me a formula already for dy over dx. So I've got 4 times the square root of the y value 3 squared plus 7 times my x value, so 7 times 1 squared. So let's see here. This is 9 plus 7, which is 16. Square root of that is 4. 4 times 4 comes out to 16. Nice. All right, so time to plug some things in. So we are now evaluating the second derivative at 1, 3. And although we never spell it out, we have a derivative, a dy over dx of 16 that we're also waiting to plug in. So we've got, in the numerator here, 4 times the y value 3. dy over dx we said was 16, so that goes there, plus 28 times my x value, which we said was 1. Downstairs we have the square root of, that's going to be 3 squared, plus 7 times 1 squared. And let's evaluate this a little bit further. So back to the numerator, what's all this come out to? Well, we've got, let's see here, we can multiply this in any order we want, so I'm going to do 4 times 16 first. I know that's 64. And then 64 times 3, well, 3 times 60 would be 180. 3 times 4 is 12, so this would be 192. Plus 28 is going to be 220. So no calculator problem. Got to use our mental math or long multiplication, however you want to play it. Down here, this is kind of familiar. We did this up here, but this is 9 plus 7, square root of 16, which is 4. So now we have 220 divided by 4. Well, let's see here. 200 divided by 4 is 50. 20 divided by 4 is 5. So this is 55, giving us answer choice C. On this one, we've got the graph of f prime up here, and we want to know at which of these indicated values on the graph is f double prime the least. So f double prime is the slope of f prime, so we want to find when the slope of f prime is either the least positive or the most negative, whichever we can finagle on this graph. So we would say the slope of f prime then is most negative because we do have some downward sloping pieces. At what spot? Well, definitely not D. That's a positive slope. A looks to be a 0 slope, so it's really down to B or C. Now between these, B looks a lot steeper than C. C, you're almost flattening out here. B, you're still going down at a pretty good clip. So we're going to go with spot B, which conveniently is also choice B. For this one, we have a curve defined by x squared equals e to the x minus y for positive numbers. We want to know at what x value, if any, the curve has a horizontal tangent. And they do have an option here for there is no such value of x, so we need to be on guard against that. Well, in order to figure out horizontal tangents, I basically need to know where the derivative of this thing, the slope of this thing, takes on a value of 0, if that happens anywhere. So let me take the derivative of this. Now, since it's very difficult here to isolate y, I'm going to use implicit differentiation. So on the left side, derivative of x squared, that's going to be 2x. On the right side, I'm going to need the chain rule. I've got the derivative of e to the something. Well, that's just going to be e to the something. But now I have to multiply by the derivative of the something of x minus y. Derivative of x is going to be 1. Derivative of y, that's going to be dy over dx. Whenever you take the derivative of something with y, implicitly differentiating, you need to multiply by a tail of dy over dx because y is itself an inner function of x. So we're subtracting dy over dx, and now at this point we have to isolate dy over dx. So the only way to do it, I've got to distribute, well, there's two ways to do it. I'm just going to distribute this e to the x minus y here. So that gives me e to the x minus y minus e to the x minus y times dy over dx. So I just distributed here. And now if I subtract e to the x minus y, and I've still got this negative e to the x minus y being multiplied by dy over dx. So I'm going to divide both sides by that. And when I do that, I'm going to switch the signs around here. So I'm going to write the numerator now as e to the x minus y minus 2x, and then I'll have a positive e to the x minus y downstairs. All right. So at this point, we want to know where this curve has a horizontal tangent, which means the fraction needs to equal 0, which means the numerator needs to equal 0. Because if you make the numerator of a fraction 0, then you're good to go. Now, we're not really worried about the denominator being 0 because e cannot have a value of 0. It always has positive values because it's an exponential function. But anyway, this equation here. Now, this is bad news on a number of levels initially. For one thing, this is not a calculator problem. So even if this was just like e to the x minus 2x, this would still be pretty tough to do without a calculator. But also, this is e to the x minus y minus 2x. We've got two variables in this equation. So this looks like really bad news. But now it's time for some good news. If we look back at the original equation here, we see that e to the x minus y is actually algebraically equivalent to x squared. Wherever I see an e to the x minus y, I can replace that with x squared. Well, here's an e to the x minus y. So I'm going to plug in x squared for this e to the x minus y. And that leaves me with the much nicer equation of x squared minus 2x equals 0. Well, this I can just factor and solve now. Let me take out an x. That's going to be x minus 2 inside. And setting each of these equal to 0, we end up with x equals 0 and positive 2. Now, in terms of x values that we're going to use here, they said in the beginning that x is greater than 0. So we can discard this answer of 0. The only answer we actually need here is 2. And if we plug 2 back in, let's see here. Does that work out? So we have 4 equals, this would be e to the 2 minus something. There's some y value that's going to make that work out. It's not going to come out undefined. So we're good to go here. So that's going to be choice C. Well, strap on your seatbelt for this one. This one's kind of a doozy. We want to know how many horizontal or tangent lines the curve xy squared equals 2 plus xy has. Now, on the face of it, this doesn't look like it's going to be too crazy. But in order to answer this question, first off, we need to find the derivative of this. So that's going to require implicit differentiation because we can't isolate y. And right away, this xy squared is going to require the product rule. So here's the box and ribbon. I've got my factors of x and y squared and their derivatives, which are 1 and 2y with a tail of dy over dx. Whenever I take the derivative of something with a y, it's an inner function of x, so I need to multiply it by its tail using the chain rule here, so the derivative of y, whatever that is. And so multiplying this out now, let's see, actually before we even do that, no, actually let me go ahead and do it. So we've got y squared plus 2xy dy over dx. All right, so that's just the left side of the equation. On the right side, 2 is just going to be 0 when you take its derivative because it's a constant. Then we have xy. Well, that's another product rule. So box and ribbon time, we've got just x and y this time around, whose derivatives are 1 and dy over dx. Multiplying those out with the ribbon, we've got and this is going to be on the right side of the equation now, so this is going to say equals y plus x dy over dx. Now we have to isolate dy over dx. So let me get all the dy over dx's on the left side and everything else on the right side. So this 2xy dy over dx, that can stay where it is. We're going to have to subtract the x dy over dx to get it over to the left side. And everything else is staying or moving over to the right side. So we have y squared, which we're going to subtract to get it over there. And this y was already there, so we're just going to say plus y. At this point, since I only have dy over dx is on the left, I can take out a dy over dx, factor it out. That leaves me with 2xy minus x inside the parentheses. And then if I divide by that, I get dy over dx equals negative y squared plus y over 2xy minus x. Okay, well, that was step one, just find the derivative. But now if we want to know about horizontal or vertical tangent lines, I mean, even just one of these would require a lot of work, but they want to know about both of them. So we have to test this for both. Now let's start with the horizontal tangent lines. If I have a horizontal tangent line on a function, that means my derivative at that spot is going to be 0. So I need to figure out where the derivative of this fraction equals 0. To do that, I need to know where the numerator equals 0. So let me set negative y squared plus y equal to 0. Now I can factor out a negative y. That leaves me with positive y minus 1 inside. And I see that this equation is going to be true if y equals 0 or positive 1. Now, before I go ahead and conclude that I have multiple horizontal tangent lines, first off, look at the answer choices. We have a choice of none, 1 horizontal, no horizontal, 1 horizontal. There are no choices for 2 horizontals. So that was kind of nice of them not to put that as an answer choice, because right away you know that something is up. These can't both be true. So how do we figure out which one's true, if any of them? We have to plug these back into the original equation. We found these by using the derivative. But the derivative, the slope, doesn't necessarily line up with the original in terms of locations and things existing. So let's start by plugging in 0 for y in the original. So that's going to be x times 0 squared equals 2 plus x times 0. And that's going to zero out this whole x term on the left, leaving us with just 0. On the right, this other x gets zeroed out. So we end up with the equation, or inequality, I guess, of a 0 not equal to 2. So 0 as a y value does not work. That is an extraneous root. It's not going to give us the location of a horizontal tangent line. Well, we have to try 1 out as well. I mean, if we tried out 0, it's only fair to try out 1. So let's see here, x times 1 squared equals 2 plus x times 1. Let's see if that works out. So this is saying x equals 2 plus x. And if we subtract the x's, we get 0 on one side again, which again does not equal 2. So both of these cases, this does not add up. So we actually don't have any horizontal tangent lines. Okay, well, that narrows it down to, let's see here, choices C or A. There's still the possibility that we have a vertical tangent line, but definitely no horizontal. So to check on the vertical tangent lines, we need the denominator to be 0. So let's set 2xy minus x equal to 0. So there's no horizontal tangent lines. Setting my denominator equal to 0 now. Well, to solve this, I mean, this is a tricky one because we've got 2 variables, but we're kind of in luck here because I can factor an x out of this. That leaves me with 2y minus 1 inside. Setting each of these equal to 0, I see that I have solutions where x equals 0 or y equals, let's see, add 1, divide by 2, so 1/2. I have to check both of these. Let me plug in 0 for x first. So that would be 0 times y squared equals 2 plus 0 times y. Well, that's just going to be 0 equals 2, which it doesn't. This seems to be coming up quite a bit here. So x equals 0 is not the location of a vertical tangent line, but 1/2 might still work if we plug it in for y. Let's try this out. So I've got x times 1/2 squared equals 2 plus x times 1/2. This is really 1/4 x on the left, and if I subtract the 1/2 x that's on the right, 1/4 x minus 1/2 x Well, that's really like 1/4 minus 2/4. That's negative 1/4 x on the left side. Multiplying both sides by -4, I see that this is going to be true when x equals -8. So there is an x value that goes with this y value, meaning there is a point that's actually on the original curve at which we have a vertical tangent line. So then we end up with no horizontal tangent lines, but one vertical. So that would be choice C. On this no calculator free response problem, I'm given this curve, and my first task is to show that the derivative equals this other expression. So in order to take the derivative of this thing, since I can't isolate y, I'm going to have to use the technique of implicit differentiation. So let me start differentiating left to right, and whenever I take the derivative of something with a y, I'm going to have to use the chain rule because y is a function of x, so I'll have to multiply it by a tail of dy over dx. So going from left to right, we've got 2x, the derivative of x squared, plus 2 plus 4y cubed dy over dx plus 4 dy over dx equals the derivative of a constant 5, which is just 0. So now let me get the dy over dx's on one side, or keep them on one side and move everything to the other side. 4y cubed dy over dx can stay on the left, as can the 4 dy over dx. Moving over to the right, we're going to subtract 2x and subtract 2. On the left side, I can factor out dy over dx, leaving me with 4y cubed plus 4 inside. And then if I divide both sides by that parentheses, I end up with dy over dx. Now this is where you have to reread the question. It says, show that dy over dx equals this expression. Well, this expression might be equivalent, but we haven't actually said that this equals this other expression. We still have to get there algebraically. So a couple more steps. We can definitely factor a -2 out of the numerator. That would leave us with x plus 1, which sort of matches what we have up here, so that's a good start. Denominator, we can also factor things out, like a 4. That would leave us with y cubed plus 1, another fantastic step. And then 2 over 4 we can reduce to 1 over 2. So in the end, we do end up getting what they told us to get. For this part of the problem, they want the equation of a tangent line to the curve at -2, 1. So they've already given us a point. For a tangent line, we just need to use point-slope formula. We still need to get the slope. Now recall from part A, and they gave us this, that dy over dx was this expression here. So let's just go ahead and plug the point -2, 1 into this first derivative and see what we get for a slope. So on the top we've got negative and then parentheses, the x value -2 plus 1. Downstairs we have 2 parentheses, and now this is going to be 1 cubed plus 1. So up top, this is -1 times a negative out here is +1. And downstairs, this is 2 times 2, so 4. So we have a slope of 1/4. Putting it all in point slope now, we have y minus the y value 1 equals my slope of 1/4, this is the m value, times x minus x1, so that'd be x minus -2 or x plus 2. On this part, we want the coordinates of 2 points on the curve where our tangent line is vertical. So recall again our dy over dx from part A. If we're talking about vertical tangent lines, we're talking about an undefined slope, a slope where the denominator is 0. So we need this denominator here, 2 parentheses y cubed plus 1, to have a value of 0. Well, we could just divide both sides by 2, so it's really y cubed plus 1 equals 0. Which means y cubed has to have a value of -1. And if we just take the cube root of both sides, we see that y must equal -1. How do I get the x values that go with that, though? Because this gives me the y value of my points, but not the x values. Well, for that, I go back to the original equation. So I'm going to have x squared plus 2y plus -1 to the 4th plus 4 times -1 equals 5. And cleaning this up a little bit, this here is really just 1. This is -4. 1 minus 4 is -3. Let me move the 5 over here as well. So that's -8 on the left side and 0 on the right. And the reason I did this is because this is a good old quadratic that I can now factor to get the x values. And it's a good thing because there was no calculator allowed on this. So two things that multiply to -8 and add up to 2. That would be x minus 2 and x plus 4. That gives me the x values 2 and -4. But now we have to actually write out the coordinates of the points. So remember, these both have a y value of -1. That's what we plugged in to get these x values. So we have -4 comma -1 and 2 comma -1. For this last problem part, they're asking, is it possible for this curve to have a horizontal tangent at points where it intersects the x-axis? Explain your reasoning. Well, there's a lot of ways to do this. I think the easiest is just going to be to figure out the places where it could have a horizontal tangent and then see if it also intersects the x-axis at those points. So here again, one more time, we're using this a lot, is our dy over dx from part A. And if I'm talking about horizontal tangents, that means that I have a slope of 0. So that means that the numerator must equal 0. So if I'm zeroing out this whole thing, numerator must equal 0, and that's going to happen at x equals -1. So the question then, since I'm asking, is it possible for this to be a horizontal tangent on the x-axis, I'm asking if the point -1 comma 0 is on the curve, because my y value has to be 0 if I'm stipulating that I am on the x-axis. Otherwise, we could have any y value we wanted. So let's plug in -1 for x and 0 for y to see if this one horizontal tangent location happens to be on the x-axis. So we're going to have -1 squared plus 2 times -1 plus 0 to the 4th plus 4 times 0 equals 5, question mark. And let's see here. So this is 1 minus 2. That's -1. All these other things get zeroed out, and we still have 5 on the right side. So does -1 equal 5? Sure doesn't. So that means it is impossible. The curve cannot have a horizontal tangent that's on the x-intercept, because this was the only point of horizontal tangency, and it does not work out if you use a y value of 0 to go with that.